Hi, this is Robert Bolaños. Welcome to an episode of FRA using TopSPICE tips. Okay, about a year ago, I did a video explaining or showing that TopSPICE had added a powerful feature called FRA, and I did a demonstration how to use it. But since then, I've learned to use it a little bit better, and I want to show some of the tips. Now, I'm going to go ahead and talk or explain what the FRA. This is coming from the viewpoint that you're not familiar with it, or maybe it's a novice or a beginning student. So, if some of the material you already know, go ahead and skip forward. Okay. So here, some of you may not know what a FRA, but the FRA stands for Frequency Response Analysis. Okay, and what this does is you're able to do Bode plots, which is a time frequency domain. Bode plots are a frequency domain, but instead of using an AC analysis in SPICE, you're going to be using a transient analysis. Okay, so this is very powerful if you're able to do a Bode plot, which is frequency domain. If you can plot that using a transient analysis, which is time domain, then you can do a lot of things with it. Okay, so next question would be, well, how does a FRA work? Okay, the FRA works by injecting a signal into the loop. Basically, when you add a voltage source in the loop, you're breaking the loop. Okay, and then the signal travels around the loop. Okay, so let me show you a representation here. Okay, so this would be like a very simplified flyback. You have your transformer, your output filter, and you have your divider resistor here. Okay, and then this is your sample feedback, PWM, and so forth. So this is a loop. Okay, typically on an actual power supply that sits on your bench, you'll add a 10 ohm or maybe a 100 ohm resistor. That's your injection site, and you'll have two test points. You'll have a out and an in, and then we use an injection transformer. Let me see if I can make that here. See if I can write that. Okay, there. That's an injection transformer. Okay, and what it does, you have a stimulus or a signal generator, and you start with a low frequency. You can start, let's say, 100 hertz, and then you sweep it to maybe a typical would be maybe 100 kilohertz. That would be the switching frequency. So you want to plot that, and you go through steps. And basically what it does, it generates a little wiggle across this resistor. Well, that wiggle is introduced there, and it travels around the loop. So once you get in here, it actually modulates. In other words, it starts modulating the trailing edge. Okay, in a sense, then that wiggle or this modulation ends up over here, and it travels back. So you're going to have two waveforms at this node and at that node. And this node, we call it out, and then this node we call in. Okay, so then we will have a channel 1 In this case, it could be a scope or a channel analyzer that will measure the out, and then you'll have channel 2 that measures and analyzes the in node. Okay, so what it does, once it has, let's say this is channel 1, and then let's say channel 2 looks something like this. Well, what it does, it measures the amplitude of channel 2, measures the amplitude of channel 1, and it divides it, and that's your gain. Okay. Then it measures the phase difference, so the difference between here and here, phase difference, or the phase shift. Okay, so then calculates the gain and the phase, and then plots it in the frequency domain, and you'll have one for gain and then one for phase. Okay, so in a nutshell, that's what it does. Okay, so what are the advantages of using a FRA using transient? Okay, well, like I had mentioned, that you can do a Bode plot, and in this case it's very useful when you do a Bode plot, because you can do a phase and gain of a closed loop, particularly in a power supply. But you can also use it like an op-amp. If you have an op-amp, you have a circuit and you want to see if it's oscillation, you can break the feedback loop and you can insert it that. So there's quite a bit of stuff that you can do FRA. Okay, and the biggie is this one here. Okay, it means that you don't have to extract an average model. So instead, you can use a, let me see, where's my, you can use a switching model. Okay, so you might ask, what's a switching model? Okay, so this would be a typical switching model. Say right here you have my input filter is up here, and then you have your transformer, your transistor. Here this is a 1, 2, 3 stage flyback, and here I'm closing on this supply right here. Here's my divider network, and here is my pulse width modulator, and the output goes back to the gate. Now if you notice here, here's my injection resistor. The top is labeled out and the bottom as in, and here is my FRA, so I have it labeled as VFRA. And then to make it work, you have to select sine, otherwise it will not work. You have to, and then you initialize it. So if you're doing a decade sweep, you would go, you can label this as offset 0. You always want it 0, and then the amplitude. Okay, you can set it to a low voltage, let's say anywhere from 10 millivolts all the way to a volt. It depends on this type of power supply that you're simulating. And then for just to get it to run, this is not important, but you have to have something here. So typically I just set this to 1K, and the sweeping is actually done in a different menu, but set this at 1K for now. Okay, going back, there we go. Okay, so you can use a switching model and that means that you don't have to use AC model. Okay, and which are those models? Well, there's the Vache-Victorian model, there's the Ridley model, there's the Kopek model, there's the Basso model, and there's the Ben Yakov model. And then the one that I've been using by my mentor is the Jack Alexander model. I'll just put Jack, which is, this is the simplest model. And it's a first order model. Okay. Okay. So what are the disadvantages? Okay, here's a disadvantage. Okay, and it may or may not be so. As computers have gotten faster, simulation times are getting faster and faster. So this may or may not be a problem. But anyway, when you do a FRA using a transient analysis, it does take a long time. Okay, and they have the same limitations that the real FRAs. And the FRAs that are out there in the market, the major players are the Venable, the Omnicron Bodhi 100, and the AP 300 from Relay Engineering. These are all very good FRAs. At work I have all three of them, and I also have a fourth one. The fourth one is the one that I use at home. Okay, so you might want to do a Google and look these up. Okay, and then the last is that there's a little thing that as you try to make your time steps smaller, if you make them too small, then your simulation time gets longer. Takes longer to do a simulation. So there's a little balance of, if you want accuracy, versus time, simulation time. Okay. Okay, here's some of the tips on using the FRA. And one of the tips that I would suggest, and this helps a lot, is do a first pass or a preliminary simulation, and you want to do it typically with all the components on initialize. Okay, what does that mean? That means that all the capacitors, or at least the important ones. And which are the important ones? Okay, well, you know what, let me backtrack. You want all the capacitors and all the inductors to have no voltages in the capacitors and no currents in the inductors. And which ones? Well, you want your output capacitors set to 0, and there's a SPICE directive, which is right here. You can double click on the capacitor and you put IC equals 10 volts, or you can click on the inductor and put IC equals 150 milliamps, whatever it is. But in this case, before you initialize them, you set them to IC equals 0 volts, or you can leave them, or just leave it out, okay, for right now. Okay. Oh, and the other one is the primary inductor. These are the ones. So the output inductor, the error amp, and the primary inductor in the flyback. Okay, so once everything is uninitialized, make sure that they're starting at 0. You simulate and you record the steady state voltages for the capacitors and the currents and the inductors. And once you know what those are, then you update with the steady state values that you recorded here. Okay, so you may have to do maybe 2 iterations to get the final values, and let me show how to do that. Just okay. Okay, so in this case, here's a capacitor. Okay, I ran a simulation, and then after I did the simulation, I measured the voltage at this node. So in this case, this should be 9.39. Okay, so I know that this node is 9.39. Okay, so I double click, and then here on line 1, IC equals 9.93. Okay, and I want to iterate or make you aware that when the value of the capacitor is on the left side, then the top lead is a positive. This would be the negative. So just remember that the value on the left means that the top is the positive. Otherwise, if this is backwards, then you would have to initialize this as a negative to flip it. Okay, so that's very important to get the right polarities. And again, you can do the same thing over here. Here's my other windings, and you can initialize them as well. You put the IC, in this case IC equals 9.55. Now here's the situation that if you notice right here, okay, this is already initialized, this is initialized. Okay, now since the value is on the opposite side, see, so this is the positive then. So instead of making this positive, I can make it negative, and it should flip it. This one also, but if you notice, it already has a negative here. Okay, and if you recall, if you notice, this is not initialized, but as long as I have one of the capacitors, in other words, I don't have to initialize both of them, I can initialize one of them. So in this case, if you notice this one, say I have negative 9.95. Why? Because the value is on the right side now. That means this side is a positive. Okay, and if this is positive, then I need to put a negative number. And if you notice, this is not initialized. Why? Because this is already initialized. Basically, you initialize the node. Okay, so now the next is you initialize also your error amp. So I have it right here. Okay, so now once you have that, then you go to your transients and you get that right here. You go to your setup, file. Okay, and then in the file, or in the menu on your transub analysis setup, you enable that. Basically you enable your FRA, you go to setup, and that should bring you this menu. Okay, so I'm going to go over this. Here is the test signal, and that's the name of your test signal source name. So in my case, the name is FRA. So I have that there. Okay, and then I can do a decade. Okay, and when you select the decade, then you have to specify the start time and the stop time, or not the time but the frequency. So that's the start frequency, this is the stop frequency. And then since you're sweeping by decades, this will tell you how many frequencies per decade. So in this case I'm selecting 4. Okay, so then you have these, and these are very important. These are probably the most important ones. So you have the time steady state, which is this number 1, and that's the time steady state. That's the time when the FRA starts to sweep. Okay, what does that mean? Okay, when you do the simulation and you're starting from 0, excuse me, if you do not initialize, in other words, if all your capacitors are at 0, okay, then it's going to start from 0 volts, and let's say this is 9.5 volts. Then they're going to start simulating, and it goes up and up and up, right? And then it may overshoot a little bit or undershoot, but then it settles. Okay, so this is a settling time. So the time where everything is at its final value, or steady state, that's the time that you want to start your FRA. Okay, now this time can be sometimes very long. If your capacitors are big, they can be as much as maybe 10 milliseconds to maybe 50 milliseconds. That's a long time to simulate, very long time. Okay, so one of the tricks is by initializing the caps and the inductors. Okay, the reason we did the IC equals 9.95 and then also initialize the inductor, in this case my inductor was 150 milliamps, was instead of the simulator starting here, the simulator actually starts with the values here. Okay, doesn't start here, the simulation starts here, so it's already at the time value. So theoretically I can start simulating over here. Okay, so I will reduce the simulation time by a lot. Okay, so this is pretty powerful in that it makes your simulation, or it cuts your simulation time by a lot. Okay, but instead of setting it way down here, I typically set it to 1 millisecond. That's good enough, and that's basically the gist of this tech tips, that by initializing you can make this steady state time much lower. Okay, okay, then the second is this one, the number of periods or cycles. This should be more, you should name this cycles, but anyway, they call it periods. And basically it's the number of cycles that you want simulated. Okay, so in this case you're gonna run a 1 kilohertz, and you're going to see 5 cycles. Okay, well, it actually depends on your TR max, which is this next number 3. Okay, so this is the maximum run time. Okay, and that's very important. Okay, because this also can speed up your simulation time. Okay, so in this case, I'm going to go ahead and set it to, actually I'll set this to I'll set it to 2 milliseconds right there. I'll change the simulator. Okay. And let me go ahead and okay, so this is what happens. You specify your TR max, which is this here. Okay, and if it's lower than your number of periods, this is the number of periods divided by the frequency. If this statement is true, then only 1 cycle will be simulated. However, if it's false, then it's going to simulate. In this case, I have it set to 5 cycles. Okay. So in this case, let's say 1 kilohertz. And I'm using these values, 5 and 1 kilohertz. This would be the test signal. Okay, so when it's 5 cycles divided by 1, it's 5. So this is smaller, right, than this. So it is true. So you only get 1 cycle. Okay, so it means that it simulates for 2 milliseconds instead of 5 milliseconds. Okay, so you knocked off 3 milliseconds right there, a simulation time. Okay, and all of that adds up. Well, let's say as you get higher in frequency, and let's say the frequency now is 10 kilohertz. Okay, well, that's 500 microseconds. This is smaller, so then this statement is false, right? And if it's false, then it's simulating 5 cycles. But mind you, now instead of simulating for 2 milliseconds, it's simulating for 500 microseconds. This is smaller. So again, it saves time. So basically, the TR limits the low frequencies to be simulated for 1 cycle, and it reduces the total simulation. So that's where some of the speed comes. Okay. So let's go ahead and run a quick simulation. Okay. So I've already explained that. Do that. 1, and I said I'm going to change this to 2. Okay. Oh, and one more thing that I wanted to add. Okay. This is very important. Okay, so if this is simulating for 2 milliseconds, then make your total time, let's make it 5 times. Let's say yeah, let's say 10 milliseconds. This has to be longer than than this. Okay, I think I got everything. 2. Okay, and then run. Okay, if you notice, this is below 2 milliseconds, so it's running fast, a little bit faster. That increased a little bit, but it should stay under 2. So now it's decreasing because the frequency is increasing. You notice there? Okay, it's getting smaller, and you notice now the simulation is going faster. It's up to 17 kilohertz. We've got a minute. $36, 56 kilohertz. A minute 12. Okay, there you go. Okay, so now this is your gain and this is your phase. I hate to see it in this 2 planes. I hate that. So what you can do is you can go to move, select that, you cut, paste. Okay, so now you have it in the 1 plane. Okay, so now let's say right here, if you notice, this is the gain and it's crossing right here. So to measure that, I use the cursors, and you'll notice like, oh, how do I measure that? I mean, I can kind of guesstimate, right? But this is difficult. Even here where the phase crosses at 0, what the heck is the measurement here? Okay, here's a tip. Okay, on your computer, press Control, hold the control down. Okay, now left click, look at that. The cursor is following my mouse. So now you can go ahead, set it right there, and there you go. So it's 3.8 kilohertz. Okay, so now press Control, right click, I get the second. Okay, go up here approximately, and I'll say that it's close to there. There I go. So I have a crossover at 3.8 with a phase of 69.88. Okay, let's say I want to change the axis. You can do that. Go to 120, change these 10. Okay, there you go. Okay, so now this that I perform is a decade sweep, but I want to show you even more powerful. I think it's probably the most important thing. Here's the problem when you do a decade. Okay, when you do a decade, your signal is constant. In other words, whatever you set this voltage source, and here I set the amplitude to 30 millivolts. Okay, so as this thing is sweeping through all these frequencies, the voltage is the same. It doesn't vary. Okay, and in power supplies, typically, since you have your gain looks like this, okay, at low frequencies, your signal has to be a little bit higher, okay, and then at the crossover frequency, you want the voltage or your signal to be a little bit lower, and then as you increase or you go into the high frequencies, you want to increase your voltage. So basically, you would want a voltage that varies with signal. So if you were to, let's say this is your V test signal, and let's say this is 1 volt. Okay, just a representation. You will want your signal to look something like this, a little higher, and then as you go approach your crossover frequency, do this, and then go up like that. Okay, so typically this is what you want. But when you do the decade, basically it's like this, straight. Okay, so how do you do that? Okay, well, what you do is you can go ahead and enter here. Let me go ahead and show you how to get there. You go to test setup, and then you click that, and then that table comes out. So here you can see I'm starting, instead of at 100, I went a decade lower. I went almost a decade. I went to 150, and if you notice, I started with 100 millivolts, starting a little bit higher, and then 300, and then decreasing, and then 500, 60, and then as I get closer to that mid frequency, then my voltage starts dropping to about 10 millivolts. Okay, and then right here at 50, I start increasing a little bit, and then I increased it up to 100K to about 40 millivolts. So there's a little dip and then a rebound. Okay, and what it does, it gives you a much better simulation. Okay, so let's go ahead, we'll click that. I think everything's done. So now if you notice, simulating at 150. Now because these frequencies are very low, they're going to be simulating and showing only one cycle, and typically in the low frequencies that's good enough. Okay, but then as you get at the higher frequencies, you want to extract a little bit more signal, so you need more cycles. That way the TopSPICE can do an FT and get some decent measurements. So anyway, it's running right now. And this should be the last one. So it's 3 minutes and about 3 minutes and 20 seconds. Okay, here you go. Okay. Here again, we can go to trace, move, select, cut, paste. Okay. So then you can change the axis. Okay. And then I want to show one other trick, just to verify that everything is hunky-dory. Okay, so here, and then you can do your measurements. Okay, now a lot of times there might be a point that is, let's say like this point, okay, or let's say there's another point. Typically you'll have noise up here in the high frequencies. Typically you can disregard that. Okay, what you want to look is where they cross, basically the crossover frequency. That's what you want to know. Okay, but if there's a point that you want to investigate and say, well, maybe the waveform got distorted, and that is possible. So what you can do is you go here, auto plot, and if you leave the FRA, it plots this again. But if you click it and then click transient, then you can see the actual transient signals. See, these are the transient signals. Okay, so if you notice, this is one cycle and so forth. Okay, and then let's look at some of the higher other ones. Let's look at 15. Copy, paste that. Okay, and then we can go ahead and zoom. See, you can see that you can see the ripple, and it looks like a little sine wave. Okay, but if you start seeing that it looks like a square wave, not a square wave, but like a triangle, a severe triangle, then you have too much distortion, meaning that you have too much signal, and you may have to run the simulation with a smaller voltage test signal. Okay, anyway, so that's a pretty neat feature that you can look at the transient that way. Okay, and I think this pretty much concludes my tips. I think with these tips you should have a much better better feel of how to set it up and get some real good measurements using TopSPICE as your simulator, at least for simulating your power supply. If you have any questions or comments, you can post them here on my YouTube channel, or you can email them to my email posted below. Requests for SPICE files can also be sent to my email address, and I usually respond pretty fast. So anyway, thank you for watching.